Implement full adder using 3x8 decoder and suitable gates. So full adder, we know that for full adder, 3 inputs and 2 outputs. So 2 outputs are sum and carry. So sum expression is A XOR B XOR C in, and for carry it is AB B C in plus C in A. Now first thing is we need to get the minterms for sum and carry. We can do this one in two methods. Either directly we can write the truth table and we can take minterms, or else by using this particular Boolean expressions also we can do it. So the first step is we need to elaborate sum. So here sum can be written as A bar B bar C in, A B bar C in, A bar B C in bar plus A B C in. Now, as it is SOP, in SOP 0 is called as bar, 1 is normal. So observe carefully, wherever there is bar, I'll put 0. So this is 0, 0, 1. This is 1, 0, 0. This is 0, 1, 0. This one will be 1, 1, and 1. Now what is the equivalent for 0, 0, 1? The equivalent for 0, 0, 1 is nothing but 1. And for 1, 0, 0, it is 4. And this is 2. This is 7. So sum can be written as sum is equal to sum of minterms 1, 2, 4, 7. Let us consider this as 1. Now let me do the same for carry. We know that for carry it is AB, B, C in, C in A. So this looks something different. So here variables are missing. So I'll do like this. We know that SOP 0 is called as bar, 1 is normal. Here this is 1 and for B it is 1, whereas C is missing. So as C is missing, I'll take don't care. Okay, so for A dot B, I'm writing like this. It is 1, 1, X. Similarly, for B, C in, so here B means 1, C means 1, A is missing. So instead of A, I'll take don't care. Next, similarly, A, C in. So A is 1, B is missing, so put X mark, and for C in, it is 1. Okay, so here as C is missing, that's the reason in third position I have kept X mark, and here A is missing, that is first position, so X mark, and B is in second position, so in the second X mark, which is nothing but a don't care. Now a single variable can have two combinations, so here X can be either 0 or 1. So remaining bit should be written as it is. Here also 0 and 1, the remaining right two most bits should be written as it is. And this is 1, 0, 1. This is 1, 1, 1. So first I am taking 0, next I am taking 1. So 1, 1, 0. 1, 1, 0 equivalent in terms of decimal 6. This is 7. 0, 1, 1 is 3. This is 7. This is 5. This is 7. So finally I got carry is equal to sum of minterms 3, 5, 6, 7. Let me consider this one as 2. Now by using these two, I'll try to plot this particular full adder by using 3x8 decoder. So we got sum is equal to sum of minterms 1, 2, 4, 7. And for carry, sum of minterms 3, 5, 6, 7. Now he is asking you to implement this one by using 3x8 decoder. So 3x8 decoder means it contains 3 inputs and 8 outputs. So take one block. It contains 3 inputs and 8 outputs will be there. 1, 2, 3, 4, 5, 6, 7, 8. Here three inputs are nothing but A, B, C in. And internally after it, like this is 0, 1, 2, 3, 4, 5, 6, and 7. Now for sum we are getting minterms as 1, 2, 4, 7. So take one OR gate and output of this OR gate is sum, whereas inputs are 1, 2, 4, 7. So 1, 2, 4, 7. This is how we need to connect. Next, for carry, take one more OR gate. Now here output is carry, whereas inputs are 3, 5, 6, 7. So 3, 5, 6, and 7. So leftover one is 0. You need to connect this one to logic 0. Okay, whereas all these remaining lines are logic high. Why I am considering them as logic high means in sum of minterms in K map we denote them with 1. Okay, so in SOP preference will be given for ones. So 1 is nothing but logic high, whereas 0 is nothing but logic low. See here, if 3 variables are there, we'll get 8 combinations, which is 0, 1, 2, 3, 4, 5, 6, and 7. Among this, if you observe in sum, 1, 2, 4, 7 is done. So 1, 2, 4, 7 is done. And for carry 3, 5, 6, 7. So 3, 5, 6, and 7. So almost everything is covered except 0. So that's why the 0 should be connected to logic 0. So this is how we need to implement full adder by using 3x8 decoder. If needed, you can put one symbol that is called as EN, which is nothing but enable. Means this enable can be either 0 or 1. If enable is equal to 0, this circuit will not work. If enable is equal to 1, this circuit will work. So simply you can take one enable and you can give 1 for this particular enable, or else don't connect this enable pin, and in note you write like this. In note we are assuming enable is equal to 1, which is nothing but logic high. By default enable will be treated as 1, or else it would be better if you mention the enable and give the input to it as 1. So simply enable and input should be 1. If enable is equal to 1, circuit will work properly, means in on state. If enable is equal to 0, the circuit will be in off state, means we will not get any outputs even though we are applying inputs.